Hello, everyone. Welcome to the Mindscape podcast. I'm your host, Sean Carroll. In science, when things are going well, there is an interplay between theory and experiment. Experimenters notice something about the world. Theorists rush to offer an explanation or many explanations for those phenomena. The experimenters go out and test the predictions of the theory. They discover even new things. The theorists are called in again, and it keeps going back and forth. But occasionally, in fact, I would say almost never, but sometimes, one can be the victim of one's own success. And that is the story of modern particle physics. In the 50s, 60s, 70s, we were just splashed with all sorts of experimental results that were very puzzling, very interesting, very intriguing, very hard to explain. We put together a theory, the standard model of particle physics. And then something happened that almost never happens in science, which is that we kept collecting data. The experimenters have not slowed down. They've not gotten worse at their job. They're probing the universe in regimes where we have not yet probed it. But the new data is still in line with the standard model, with the theory that we put together back in the 60s and 70s. The capstone of this, of course, was the discovery in 2012 of the Higgs boson, something that was predicted to exist back in the 1960s, with more or less the same properties that we'd predicted it should have back in the 1960s. Despite that success, there are plenty of reasons to think the standard model is not the final answer. Of course, it doesn't include gravity as a fully quantum mechanical theory, but also, what is the dark matter? Why are there so many particles? Why do they have the numbers that they have? Why is there more matter than antimatter? A whole bunch of questions that are looming over the standard model. Or, to think of it as a physicist would think about it, there are clues that there must be deeper stuff going on than the standard model of particle physics. And despite this wonderful ability of experimentalists to come up with new experiments looking beyond where they've looked before, it's hard to keep that project up in fundamental particle physics. It's expensive. The timescales are very, very slow. It's a different kind of problem. Every science has its own idiosyncrasies. But in biology, if you're working with a little C. elegans roundworm, you can go in there and change its genome and make it do something that has literally never been done before, at least as witnessed by human beings. In particle physics, it is very, very difficult to do an experiment that probes into a regime where human beings have never probed before. You need a lot of money, a lot of engineering know-how, and at this day and age, you need a lot of political will. It's a more than one country kind of international collaboration to get this going. So the question is, the Large Hadron Collider was super successful as a machine. They found the Higgs boson, Nobel Prizes were given out. I would like one more Nobel Prize to be given out to the actual experimenters who were responsible for that, but we'll see whether that happens. The question is where to go next. What are we going to do? We're in this weird position, a theory that fits the data, but we know, or we strongly think that it's not the final theory. So there's different programs on the board, different proposals for what to do. The folks at CERN, which is the home of the Large Hadron Collider, would love to build a larger Hadron Collider or Electron Collider or something like that on their site. There are people in China who want to build an ultra-high energy machine. We're not sure what we're going to do next. Today's guest, Cari Cesarotti, is a particle theorist. So she works on building models of new kinds of particle physics that could then go out and be tested. But she's especially interested in literally the experiments you can do and figuring out what are the best experiments possibly that you can do. So rather than sitting back in the armchair and thinking about quantum gravity and the emergence of space-time, as some people are wont to do, she wants to make predictions and then go test them in a very, very detailed way. And the particular way that she is most fond of is colliding muons together. Muons were discovered back in the 1930s by Carl Anderson. There's a brief moment in the 1930s when Carl Anderson, a physicist at Caltech, had discovered half of the known particles in existence, because before Anderson there was only electrons, protons, and neutrons. And then he discovered the positron, the antiparticle of the electron, as well as the muon and the antimuon. And the muon was the particle that led I. Rabi to say, who ordered that? It was not clear what purpose it served. It was not part of the atom or anything like that. Of course, today, there's plenty of things that are not part of our everyday human existence, but they're there, out there as particles. Muons are heavier cousins of the electrons, so they have a lot of benefits that electrons have and protons have. They're kind of a happy medium in between them. Massive like the proton, but easy to control like the electron. So why not build a machine? Well, sadly, the muons decay in about a microsecond. That causes some technological challenges, and it's plausible that we are right now at the verge of being able to address those technological challenges, opening up the possibility of building a muon collider and testing physics beyond the standard model of particle physics in a way we've never been able to do before. Cari's going to give us the sales pitch for doing that, and I hope you come away convinced that this would be a wonderful idea. So let's go.
Hi, Sean. Thanks for having me.
So the standard model of particle physics, this is what people like you and I think about a lot these days. Let me ask like a silly question to start. Do you think that the standard model is beautiful, or is it kind of an ugly duckling as theories go?
Ooh, interesting question. I've never had it quite posed like that. I think in some ways it is quite beautiful in the sense that there's a lot of patterns that we see. And in physics, really the thing that we love to see is patterns. So we see that there are three generations of a lot of things. We see that the gauge bosons kind of fit nicely in one bucket. We see that there's the pattern of things getting heavier and things coupling more strongly to the Higgs. So in that sense, it is a very beautiful model. But in the bigger sense of where did this thing come from, it's very ugly in the sense that there's not really a fundamental explanation as to why particles look and behave the way that they do.
Well, let's just be nice to our historian listeners or whatever and explain what a gauge boson is and why you say they go into a bucket.
Fair enough. Yeah, so in the standard model, there are basically two kinds of particles. They're either fermions or bosons. So the fermions are the things that tend to make up matter. Things like electrons are fermions. Things like quarks, which are the particles that you find inside of nucleons, are fermions. And then the gauge bosons are the particles that effectively tie everything together because they mediate the forces exchanged between these particles. So fermions, often we like to think of as matter. If they live long enough to survive, then they can be stable matter. And then the bosons are the force carriers. So things like electromagnetic fields, the particle description would be made out of bosons.
And the standard model that's the label. It's such a boring label. I mean, it gives you the impression that it's just the model we have today and tomorrow we're going to change it. But there's a little bit more stability here.
Yeah, I mean, that's kind of funny. Whenever I think of standard model, I kind of think of like the most beautiful, the most beautiful model, the standard model, like the thing that you would think of when you consider a beautiful person. It's like, yeah, okay. So interesting that you have that. But I mean, yeah, so the model is inherently something that it's not supposed to be a first principles object, right? It models the things that we see, but it doesn't come from a deep, a core principle. So in the sense that, yeah, it could move around if we find something that's in conflict with our current model. That's true. But so far, it's done an amazing job at actually accounting for a lot of the physical phenomena we've been able to see.
Actually, that's something worth amplifying on because maybe we don't always make it clear to folks, but the difference between a model and maybe a theory or a framework, right? I mean, we have quantum field theory as a very broad framework, and then this very specific thing of the standard model.
Yeah, I mean, so this is a really subtle question that I feel like you kind of roll your eyes at the first time you're taught this distinction in school. But yeah, a model is something that we use to account for phenomena that we observe. So it's very empirical in nature, right? Like the standard model, we don't necessarily know why there are three generations of everything, but we observe them. So they go into the standard model. Versus something like grand unified theory would be a way of explaining sort of why everything comes together in the way they do. So certainly we can't talk about the details of grand unified theory if we're going to talk about other things. But yeah, the difference is, like you mentioned, that something is first principles to motivate where it comes from versus something that's a way to kind of categorize empirical evidence that we've seen.
And the standard model of particle physics, as we call it, it does a pretty good job of accounting for what we see.
It does a frustratingly good job, Sean.
Tell us what that exactly means. Why is that frustrating and how good is the job?
Yeah, so I mean, the kind of work that we do as particle theorists, right, is we want to basically stress test the standard model and either confirm very rare predictions that it can make, and so sort of see very hard to see phenomena show up in things like colliders, which is my personal specialty and realm of interest. And then also we want to see where it breaks, right? We want to see if there are pockets of predictions that are false or that are just lacking, or we see some phenomena that's unexplained by the standard model. And that's where it's fun to be a researcher, right? Is when you try to come up with solutions to why this prediction isn't quite matching your expectation.
But it's a weird thing, right? I mean, we have a theory that fits so much data, and yet we're convinced it's not right. Like, why don't we just declare victory and do biology?
I mean, fair enough. And I think, in fact, a lot of people have had that mentality. But there are some pretty big holes in particle physics. And I think kind of the phase transition that we've gone through as a field in the past few decades, certainly in my career, which has been, albeit not quite as prolific as yours, Sean.
You're younger.
But yeah, I mean, there's big open questions that are becoming more and more sort of nuanced versus like, what the heck is this? Right? Like that used to be the state of affairs, is that we'd turn on our little bubble chambers and we'd look at something and be like, what the heck is this? And that was a really rich, interesting time to be a physicist. And a lot of theories came and went. And we were able to make an amazing amount of progress in such a short period of time just from experimental evidence, right? And now I think we're in a much more subtle phase of particle physics where the questions are not so much, what the heck is this? But where does this come from? Why does this look like this? What are the things that we're not seeing? Like things that are much more fundamental towards why has the universe taken on this profile?
And I think that, in certain corners of the internet anyway,
oh no,
it's a big internet out there. There's a lot of corners to it. But there are people who worry, they would almost give you the impression that the slowing down of discoveries in fundamental physics is somehow physicists' fault. Like you're not doing it right. And I try to explain that's not really it. Do you have a favorite way of conceptualizing this?
Yeah, I mean, it's so funny that you say it like that, because in some way I feel a bit flattered to think that people think that, my work is so important that I can that anything consequential could be the fault of mine. And it's like, well, thank you. My goodness. But I mean, yeah, it's physics is a field that I think has always kind of suffered from being something that the public really enjoys as much as something like astronomy or biology, where people either see or experience much more of it. Because physics requires, as we are already seeing in this conversation you and I are having, right? Physics requires so much lead up to understanding sort of why it's surprising or exciting or interesting or puzzling, right? So I think that a lot of this rhetoric comes from the fact that the LHC turned on and we just saw the Higgs boson. And it's kind of a ridiculous sentence to me to say, we just saw the Higgs boson, because this was like the linchpin to making sure the standard model was even first order correct. So yeah, I mean, like the answer is just that there's not new particles showing up with sort of the unexpected frequency, which they were in sort of the 50s to 80s. And who ordered that was kind of the motto of particle physicists. But to say that that's a failure versus just the field has matured a lot, I think is underselling all the work that people have done for the past 70 years.
But there still are looming questions, and you used maybe the perfect word here when you said they're subtle questions, right? It's not like here is a picture in our experiment that we can't explain. It's like we have a feeling there are deeper explanations and there are reasons to go look for them.
Yeah, absolutely. So sort of the jargon that you might hear people use in particle physics is the hierarchy problem. And if you are not thinking about it all the time, it's kind of easy to write off as, well, is this really a problem, or are you just looking to keep yourselves relevant? But, effectively, how I like to describe it is, I loved all the sitcoms from the 90s or whatever, where it's like, oh no, like something is going to close unless we find $35,629.15. And then behind them, you see the banner that's like talent show, grand prize, $35,000, $629.13. I think that was the same number. But yeah, like the fact that there are numbers that for some reason are so big and yet agree down to such a small accuracy is something that should be
Right.
fundamentally puzzling, right?
Good. So let's be a little bit more explicit. Now, we've you sopped to the historians out there. Now, for the physics enthusiasts, what are the specific problems? You mentioned the hierarchy problem. What is this?
Yeah.
That sounds like politics, not physics.
I mean, these days, kind of hard to disentangle, honestly. Yeah, so the hierarchy problem is something specific to understanding the mass of the Higgs boson, which is one of the bosons in the Standard Model. And the Higgs is the weirdest particle in the Standard Model by far. It is the only particle that has the properties that it has. So, like I said earlier, a lot of particles sit in 3 generations. The Higgs boson does not. The Higgs boson stands as a very weird outsider that you may have heard is responsible for giving particles mass. And if you want to learn all about that, there's a beautiful book by Matt Strassler that you should definitely check out.
Very good.
But the Higgs boson gives particles mass, has different, what we'll call, intrinsic properties. It's called the spin in specific that doesn't match any other particle. And because of that, effectively, we think that the Higgs boson should have a mass 10 to the 18 times bigger than it does. And so this is the hierarchy problem. And the hierarchy is just the mass scale that we expect and the mass scale that we see everything else sitting at. And the fact that there's 10 to the 18 differences, I mean, really 10 to the 32 because it's squared and that's the real first principles number. The fact that something can be off by 32 orders of magnitude from our theoretical predictions, where did that come from, right?
Right. But okay, I'm going to be a little bit unfair to you. I mean, you use words like what the mass should be
Yeah, of
and
course.
things like that. I mean, how do you know what the mass should be? What gives us that expectation?
So this is definitely questions that when I was in high school, so I was in high school right when I was ending high school when the Higgs boson was discovered. So if you guys want to calculate how old that makes me, please don't. But yeah, I remember having this exact same thought when people were like, oh, but is it the Higgs? Did we really
Right.
discover the Higgs? And I was like, well, who cares? You discovered a particle and it's right where you thought the Higgs. Like, why do you get to say, oh, is it the Higgs? And the truth is, like you said earlier, is that there are a lot of ways in which we can have actual predictions using frameworks and not just models. So the model is the thing that the mass that we observe is plugged into, versus the theoretical framework is in how we make the predictions. So given the properties that we hypothesized of the Higgs that make it a particle that could in fact give mass to other particles, then we have the theoretical tools to make a prediction of what the mass should be. And so basically, because the Higgs matched the properties that we modeled it to have, then we can actually use a theoretical framework to calculate what its mass should have been if things were as simple as we hypothesized to be.
Good.
So the fact that there's something going on that we don't quite understand is one of the biggest open problems of particle physics to me.
Okay, good. So that's the hierarchy problem. There's probably a bunch of other problems there. Dark matter is the obvious one. So you've thought
Dark
about
matter
this.
is for sure. And I feel like it's kind of unfair for particle physicists to claim this as strictly a particle physics problem because it could be astro, it could be cosmology. Like there's a lot of different buckets in which you could put the dark matter problem. But certainly if dark matter has a particle description, that is also something that the standard model should try to sort out.
And do you worry that much about neutrinos and their masses? Those are actual discoveries that we made over the last 25 years, right?
This is the biggest fight I've gotten to with my PhD advisor. Is neutrino mass new physics or not? Because one could argue that there exists a way to account for neutrino masses in the standard model. But my response to that is you can't do it with only fundamental interactions. You have to have something that happens a little bit more complicated. So because there does not exist a fundamental interaction term that we can write down for neutrinos that give them mass, because it won't work the same way as the other particles with the Higgs boson. Because that's not true, I think that is an example of new physics. However, I don't want to start a fight on that today. So maybe another day I'd be happy to start a fight. But yeah, neutrino oscillations, inherent violation of lepton number. something else is going on there, right? Absolutely.
Well, okay, let's indulge ourselves then a little bit and try to figure out if we can explain why you can't give neutrinos masses the same way you give electrons or quarks masses.
Okay. How do I say this without talking about left-handed and right-handed fields?
Or talk about left-handed, right-handed fields. Go for it.
Okay. So what we've seen in the Standard Model is that there exists left-handed and right-handed fields. And this is sort of the fundamental difference between massless versus massive particles, is the amount of what we call degrees of freedom, which you need to have an object sort of propagate. Um, so for massive particles, they have a left and a right-handed component. And you can think about this, I think, with sort of relativity is the best way to sort of understand it. So if you have something that's got angular momentum, let's say that it's turning to the right. If something is massive, then you as an observer can boost yourself either in front or behind of that object. And if you are in front, you see it turning one way, and if you're behind, you see it turning a different way. So you need to have an object that allows to spin both to the right and to the left to be able to describe that in nature. However, if the object is massless, then it is traveling at the speed of light, and there does not exist a valid frame in which you can boost to flip that spin. So this is why you don't need both a left and a right-handed spinning degree of freedom to describe these particles. So in our Standard Model, we have left and right-handed degrees of freedom for all of the quarks and the electron and the muon, which is my favorite particle, and the tau. But we do not have that for the neutrinos. For the neutrinos, we only have left-handed field components. So if they were to get mass, you would need to have either two neutrinos and two Higgses interacting, which is different from the fermions, which is just one Higgs and two of the fermions. But that presents, that's something that we have not been able to verify if this is right. So neutrinos could be what we either call Majorana fermions, where they don't have to have this left and right-handed story, or they can be Dirac, where they do have a left and right-handed story, and we just haven't found the right-handed component of the neutrino yet.
Good. So
I don't know if that was way too technical or not.
No, I think it was goodly technical. I like it, but maybe we can boil it down. So there's in the Standard Model for the other particles, for the other fermions, we know they have a right-handed part and a left-handed part. And then the Higgs sort of glues them together and gives them mass.
Exactly.
For the neutrino, we know they have a left-handed part.
Yes.
And the right-handed part is not necessarily there, but you need it to make mass, or you can be more tricky.
Yeah, so if you want it to basically have the same sort of mechanism as the other fermions in the Standard Model, which would make sense because, again, as physicists, the thing that we say is beautiful is symmetry. If you want it to have a left-handed and right-handed component, then we just need to find a new particle that is the right-handed neutrino, and then it could get its mass through the Higgs, and things could be similar but a bit different to the rest of the Standard Model. The other option that I said before, to do perhaps what's Majorana fermion instead, is that you don't need the left and the right-handed, is that the neutrino, you just need the 1 degree of freedom in the neutrino. And then if you have 2 of those degrees of freedom put together, stitched together with 2 Higgses, then you can also have the same sort of mass-giving mechanism. But again, that would look very different from the Standard Model. So the fact that, all the particles get their mass one way, except for this one kind of particle, which gets their mass a different way, that's still a very interesting question. And to understand how that came to be is something that would require further study.
Right. Okay, so very good. So along with the hierarchy problem, neutrino masses, we can come up with theories that explain them, but they're pointing toward things that we haven't yet found. This is what motivates people like you to continue on the search for new particle physics.
Yeah, and we haven't found we haven't found definitive evidence that a single fundamental interaction could explain this. And I think, as particle physicists, we love when there is a functional description, which again is the Standard Model, but to have a fundamental description, I think that's really what we all chase.
Good. Very good. And the last thing I wanted to mention were muons. You've already mentioned them. I'm not sure if this counts in your mind, but The muon is basically the heavier cousin of the electron. And then there's the tau, which is the heavier cousin of that. And one can ask, why are there three copies of all these particles? Is that one of the puzzles we worry about?
Oh, absolutely. Yeah. So this puzzle comes in a bunch of different names. I think to kind of put all of them into sort of one area that we could describe it, it's kind of the question of flavor physics.
Okay.
So, I don't suspect particles have that different of taste, but what do I know? So flavor is just sort of another name that we give to particles to describe how properties are different. So, charge is the one that we all learn in school and that we're most familiar with because there's plus and minus charge. But particles have a lot of properties and we just kind of need names for them. So flavor is the name that we tend to give the different generations of particles. So muons are a different flavor than electrons. Again, how they taste is not something I can comment on. But yeah, so we call this sort of the flavor physics is sort of the study of understanding why the different generations behave a bit differently.
And so what's the answer to all these questions? I mean, I know that supersymmetry was out there.
Sean, if I knew.
You would reveal it on this podcast, I'm pretty sure.
And the Nobel Prizes would come showering upon me.
And I would be in your acceptance speech,
thanking me. I think we'd have to share it, honestly.
But okay, for a long time, the particle physics community was very excited about supersymmetry.
Yes.
And they were hoping to see it at the Large Hadron Collider, et cetera. Maybe enthusiasm has cooled for that, but not completely gone away. What is your take?
Yeah, so supersymmetry is a pretty well-named thing in particle physics. It's like taking the symmetries that we have, but then more. So it's supersymmetry. And basically it's adding one extra symmetry into sort of our description of space-time itself. And then the consequences of that tend to be, in the simplest description of it, is that all the particles we've seen in the standard model have what we call very cutely superpartners. And basically they're the same particle with very similar properties, except for fermions become bosons and bosons become fermions. So supersymmetry was an amazing idea for a lot of reasons. One, because it introduced an extra symmetry, which again, we all love. And if there's a way for a symmetry to exist, oh boy, do we want it to exist. And the problem that it really famously addressed is exactly this hierarchy problem, is that if you want to understand why you have a very, very big number as a prediction, but you see a very, very small number experimentally measured, the easiest answer is there's a symmetry that cancels something, right? It's a symmetry is a fancy way of just saying that there's basically a copy of something. So the symmetry is a way of explaining why two big numbers should almost exactly cancel. So supersymmetry, as we could have seen it before the Large Hadron Collider turned on, would have been an amazing way of explaining why the Higgs boson has a mass of around 100 GeV instead of 10 to the 18 GeV. So that was kind of the most exciting promise, is that there was a fundamental reason why this particle was so light, and there was expectation of all these new particles that we would hope to see. And it was, going to be an amazing time. And people were even worried that we couldn't find the Higgs boson because there'd be too many of these other super partners. And unfortunately, we turned on the LHC and we did not see the super partners. So supersymmetry, as theorized in its most beautiful, pure form of having the maximal symmetry, is not something that's probably realizable at this point. However, there are versions of it in which you can sort of introduce new particles or new interactions that sort of take you away from that perfectly symmetric case and sort of break the symmetry. So, of course, these theories still exist and it's still worth looking for, assuming that we have the tools to do so. But at some point, you're not solving the fundamental question that you asked, or you have to introduce something that basically replaces the fundamental question that you were asking. So it becomes a bit of a patchwork solution rather than a global solution. And that's something much less attractive.
So if we were having this conversation 20 years ago, you might have been very excited about your supersymmetric grand unified theory that was going to predict, that was going to solve the hierarchy problem and give you the right dark matter and explain neutrino masses, and evidence for it would be existing at the LHC, and that did not happen.
Yeah, I mean, it is definitely something that really is a marker of a very healthy theory in physics, I think, is when it can sort of address many problems at once versus just, picking one problem and trying to, like I said, patchwork it. So yeah, it was a really beautiful theory that had a lot of reasons to be motivated, could address a lot of questions that we had about the standard model. Um, and yeah, the fact that we didn't see it, I think, has put us into a little bit of a crisis in terms of the theory world and the particle physics community.
But it is, you can see why it's a little frustrating. I mean, the puzzles that you've talked about sound like to me a very good motivation for the need for new physics out there. And we could have found it all at the Large Hadron Collider.
We could have had it all.
And we didn't. And it's not that we disproved the theories, right? I mean, supersymmetry could still be right or whatever. It's just that they're hiding from us.
Right. Yeah, and I mean, it is. I think in particle physics, certainly if you look back at the history, there's been a bit more of a give and take between theory and experiment, and so we were functioning for a long time before the Large Hadron Collider came on. We had the Tevatron at Fermilab, which was really, did make important discoveries too. But really going up to that sort of energy frontier that we could have with the LHC was so important for the field. And we were really driven by theory for a long time. And we had this beautiful promise that there was going to be something at 100 GeV, right?
Yeah.
We had many predictions that were just fundamentally breaking down that told us there had to be something up there. And we hoped it was the Higgs, but it could have been other things too. But we knew that there was something up there. And now we just don't have that theoretical promise, right? Is that we just know things are broken
Yep.
and we haven't yet been able to debug the standard model. So yeah, to me, it kind of feels like now it's the time to let experiment drive a little bit and see what's up there. And maybe as theorists, we can look at data and get inspired again for what might be a good solution.
Is there still room for the Large Hadron Collider itself to discover new things?
I am of the opinion that yes, the Large Hadron Collider is definitely still a machine that has some discovery potential. I think we have this kind of picture. Certainly, people who know a little and not a lot about collider physics have an idea that, the Large Hadron Collider just turns on and then it's like this Boolean output, like new physics, no new physics. And there's just so many subtleties that occur between colliding the particles and a physicist understanding what's going on, right? So the way that we choose what events to look at, the way that we analyze, the way that we analyze the events, the way that we interpret the events, like there's so many things in which you could introduce a bias that would skew you away from understanding fundamentally what physics could be going on. I don't think that it's probable that we'll discover something new at the LHC. But is the question, could there be hints of something new? Absolutely.
And it's even possible, following what you sort of alluded to, that the LHC has discovered something new, but we haven't quite analyzed it in the right way to notice.
Yeah, and this is kind of what I did my PhD on, in fact, is the idea of how we can sort of robustly look for new physics effects. Because again, we're likely not going to get, at this point with the LHC, we're not just going to see some beautiful new resonance just falling out at a perfect sharp peak at like 2 TeV. It's possible, but it's probably pretty unlikely. So you kind of have to use more fundamental theoretical tools to say, where are inconsistencies possible to show up versus let me just wait for the most beautiful evidence of new physics to fall into my lap.
Good. Well, that's good. This is going to keep you employed for a little while. That's
That's
nice.
what I hope.
So let's allow ourselves then to be starry-eyed and optimistic and imagine
Always.
that we're going to build new particle accelerators to go beyond what the LHC does. Maybe to soften us up, could you explain sort of the fundamental difference between colliding protons and other hadrons together versus colliding electrons and other leptons together?
Yeah, so this is a great question. And every time, certainly as a PhD student, when I listened to it, I would hear someone describe one machine and be like, "Well, this is the best collider," and then I would hear someone describe the other one. I'm like, "No, this is the best collider." And the answer is they both have strengths.
Yeah.
So when you collide something like an electron, you're basically just colliding electrons. It's a fundamental particle, so electron plus electron combines. Usually we do particles and antiparticles. So you have E plus, E minus come in, collide, produce a charged neutral state. And all of the energy of these two electrons colliding can be recombined into different massive particles, different momentum particles, as long as the net energy and momentum of the event is conserved. However, for protons are actually a big bag of stuff. And that bag includes the three quarks that usually we talk about when you first take your nuclear physics course or whatever in school, right? I
Yep.
don't know if many schools have nuclear physics, but chemistry. Let's say chemistry. You have up and down quarks, basically are the primary constituents of protons at low energies. But these quarks are tied together with gluons, and inside the quarks, inside the protons, especially as you start cranking these things up to really high energies, is the bag becomes much more complicated. And inside these protons, we have particles that are very cleverly named as partons because they are parts. And particles have to end in on. So partons.
There you go.
Yes.
I think that's Feynman's fault, right?
Well, he did enough good things, so we can give him a break for this one. But inside this proton, all of these different partons, which include the gluons, which are those bosons that we talked about earlier, and the quarks, they kind of share the total energy of the proton. So at the LHC, we collide protons of 7-ish TeV, and no one particle inside that proton is going to have anywhere near 7 TeV. Tends to happen that the gluons take most of the energy, and then quarks also take some of the energy. So when you're really looking at a collision, it's a gluon-gluon collision or quark-quark collision. Or even in the proton, sometimes you can have quark-antiquark pairs pop into the vacuum or pop out of the vacuum and then disappear again. And sometimes you can collide those. So you can have a quark-antiquark interaction. And all of these things will share the energy of the proton. So in some ways, that makes for a super interesting collider because the opportunities of what kind of particles you can collide is much bigger, right? You can collide not only up and down quarks, but strange quarks or charm quarks or gluons, and some things more rare than others, of course. But it means that you can see all sorts of interesting signatures come out. The downside is that you never know exactly what the energy of these things are. So that can make your analysis much, much harder. And of course, you don't get that full energy of the protons. So even though the LHC runs at 14 TeV, we don't actually get to see any collision happen at 14 TeV. It's usually much closer to 1 or 2.
Whereas if we collide electrons together, we can know exactly how much energy is going into them.
Yeah, often you'll hear these two machines sort of described as electrons are the precision machine because you can get everything's very clean, right? Like you just have electron in, and then you know the energy, and the collision can be basically completely reconstructed, assuming what comes out. Versus for protons, it's like smashing cars together. There's debris everywhere. You don't know exactly what collided into what. And, it's kind of like hitting something with a big hammer and just a bunch of stuff can come out, but knowing exactly where it came from and how it came to be is a much harder question. So protons are called electron is precision, and then proton is often called discovery because you can have all that high energy available to you.
It would seem that we're in a discovery kind of mood right now. I mean, precision sounds like it's good for studying things we've already discovered, but now we would like to discover some new particles, no?
Yeah, so that's a great point. And maybe the way that these things are named is kind of unfair to E plus E minus machines. So like we were talking about in the beginning with the standard model, part of understanding the standard model is knowing to what degree our predictions are correct, right? Because in science, you never get to say definitively, oh, this number is correct. You can only measure it to a certain precision. And that's sort of the claim that you can make. So with precision machines are standard model machines in the sense that they try to measure standard model things, but they are also discovery machines in sort of a roundabout way, in the sense that if you were to discover something that is not matching the standard model prediction, that's a hint of a discovery, right? So it's not, you don't get to actually physically make the particle and point to it and say, look at this, we did it. But you get to say, okay, there's a discrepancy in our data, and this could be indicative of new physics. So I guess that's why, we call it precision versus discovery, because it can't concretely define unambiguously that there is something new going on, but it can absolutely help us sort of know where to look when we go to the higher energies.
So in other words, there's so many predictions made by the standard model of particle physics that you can test them all. And if any one of them is discrepant, you determine that there must be new physics, even though maybe you don't know what it is. But then the theorists will have a field day, writing papers about what it could be.
Yeah, absolutely. And even if something's not new physics in the sense that there's a new particle or a new degree of freedom that we haven't accounted for, the fact that there could still be new phenomena that we haven't understood is still, of course, a super exciting discovery to make.
And are there plans or at least sort of ideas on the drawing board for building either higher energy proton colliders or electron colliders?
Oh boy. So this is this is the question of the decade for collider physicists. So there are a couple different ideas that people want to get into. So we can go as slow or as fast through this part as you want. But to summarize quickly, there are basically three kinds of machines people want to think about making. One is a linear E plus E minus collider. So you collide electron-positron or electron-anti-electron at reasonably high energies, so around a TeV or so, or maybe just near the Higgs mass to make a bunch of Higgs bosons. But you collide them in a line. So you don't get to circulate, you just collide them in a line. They either collide or they don't, and that's the end. Another option is to use circular colliders. So this is what the LHC and the Tevatron were, is that you circulate these particles. So if they miss their collision, they still have another chance. And if you ever studied electromagnetism in school, you know that putting things in a circle is very different than putting things in a line. So that comes with its own complications, and we can certainly get into that. But in terms of circular colliders, we either think about doing a lepton collider, so either electrons or my favorite, muons, which are certainly an immature technology, or doing protons. So basically doing a bigger, badder version of what we can do at the LHC.
If you were a betting person, putting aside
Which
the
I
muon
am.
collider, the muon collider we're going to get to, that's the payoff here. But what is the leading candidate for building the next collider other than the muon collider?
So since these are pretty big scale projects, and since we are kind of in this exploratory range of particle physics, I think that the attitude that a lot of these funding agencies and lab directors and experimentalists who actually want to see things happen versus just be like me and dream with a Mathematica notebook. I think given this climate and the fact that we can actually study a lot of Higgs physics with somewhat low energy things, I think the current attitude is to focus on lower energy circular electron colliders. And sort of the two places in the world that are presenting the most on-shell concepts of these projects would be China with the Circular Electron Positron Collider, and CERN with the Future Circular Collider, or FCC, and then the FCC EE, so Electron-Electron Collider. But of course, one day it might not be future, so we'll have to rename it. But that's what it is for now.
I love how Cari, you use the idea of being on shell as just like a common adjective that people would know.
I mean, I talked to a lot of physicists, Sean.
Okay, I noticed that the United States is not included in there. Have we basically dropped out?
I mean, so for this next round of experiments, the thing that the US has chosen to invest in right now is neutrino physics. So Fermilab, which is sort of our flagship particle physics laboratory near Chicago, Illinois, is committed to doing a big experiment called DUNE, and that's sort of measuring neutrino properties. So the lab will have to go through a lot of updates in order to make this experiment the most efficient version that it can be. And that leads us for a lot of possibilities for doing things like research and development at Fermilab. But I think that in combination with the fact that other big laboratories in the world are willing to and have put a lot of time and effort into sort of making a more concrete plan. The US is not going to be likely where we have the next E plus E minus circular collider.
And just so for sort of cultural enrichment purposes, Fermilab, which was the home of the Tevatron, which was for a long time before the LHC came on, the highest energy particle accelerator out there. The Tevatron is now just shut down. It's in mothballs, right? They don't keep running it, even though the next thing is turned on.
Yeah, that's right. So I remember I actually grew up somewhat near Batavia, where Fermilab is. So when I was in high school, and I was just a fan of physics, I had this great T-shirt that was like, "Ah, the Tevatron, like 10 years running, woohoo!" And then like the next year, they announced like, "Well, we're shutting it down for the LHC," and I was so heartbroken. I'm
Aw.
like, why would they turn it off? Like, but I mean, yeah, these things are not cheap to run.
Right.
And the fact that some other experiment could be doing basically its physics program more efficiently and then also more means that, yeah, it's probably not great to have too much repetition for these kinds of experiments. The Tevatron did a lot for particle
Sure.
physics, but now that the LHC had turned on, it just makes sense to sort of let it carry the torch.
Okay, and then we have the possibility of a collider using muons, which is kind of a compromise. Like muons are heavier than electrons, but they're simple, unlike protons. So is that a good way to go?
Yeah, so this is to me what I think will be the future of particle physics. So an E plus E minus machine is very safe in the sense that we basically know how to build it. And we think that we have all the technology that we already would need to be able to make it to work the way that we need it to work. A muon collider is a big risk, big payoff kind of machine. And of course, as a theorist, I get to just say, of course we should invest in this because because
E-
my whole life is dreaming,
Easy
Sean.
for you to say, yes.
But yeah, a muon collider is a really exciting new option because, like you said, it sort of combines the aspects of being both a precision machine because they are fundamental clean objects. You're not colliding bags of stuff. You're colliding two individual particles. Um, and because a muon is heavier, we can accelerate it to much higher energies than electrons. So an electron circular collider really can't surpass more than a couple hundred GeV. Even going up to more than 300 GeV for electron electron is a big ask. And knowing if we have the magnet technology and even just the power to be able to do that is not clear at this moment. So with a muon collider, is that you can break that frontier of higher energies than we've ever been able to go. You can do it in a circular machine, and you can do it in a somewhat clean environment, given the fact that muons are fundamental particles. So when you hear this kind of stuff, I don't know how you could not be excited, right? It's such a beautiful promise of everything you could want put into one collider.
Well, that's because you have not yet told the audience that the typical muon decays in about 2 milliseconds.
Yeah, well, that's kind of a bummer, eh?
Microseconds, sorry, microseconds.
Yeah, so the thing with these higher generation particles is that because they have all the same properties as the lower generation particles, if you want to be fancy, we'll call them quantum numbers, um, and they have higher mass, is that they have this really unpleasant tendency to want to decay, which is why atoms are made out of electrons and not muons, because muons, like you say, live for 10 to the minus 6 seconds, and then they decay away to neutrinos and electrons. So one of the most fundamental challenges that we would have to overcome if we were to make this amazing new machine would be to accelerate particles that decay, which we have never even tried to do on this kind of scale before.
So you have a millionth of a second to make a muon, to hopefully make more than one muon, make a whole
Hopefully.
bunch of them, gather them up and accelerate them around a ring that is kind of big and then collide them together. That's the challenge.
Yeah, and when you say it like that, not so bad, eh?
Well, it's
Just be quick. It's fine.
make no small plans, as a famous Chicagoan once said. How do you make all these muons? Let's get into the nitty gritty of pretending we're experimentalists. We can do that because we don't need to worry about all the details. But
That's right. Yeah. So this is already hard. So what we would need to do to make all the muons, we produce them as tertiary particles. So usually, what would happen is if we
that
have
sounds
protons.
scary already. Yeah.
I know. With protons or electrons, right? Basically, you just ionize things, and there's all your particles.
Yeah.
They're stable, they're abundant. But with muons, what we do first is we need to accelerate protons to pretty low energies, so order of a couple GeV. And again, for reference, at the LHC, we collide things at TeV, so 1,000 times slower than what we do at the main collider, but still with some acceleration technology. So we accelerate protons to a couple of GeV, and then we just dump it into some chunk of metal. So sometimes lead, sometimes tungsten. The chunk of metal that we dump into is, in fact, a very sophisticated field of research. So my apologies to people who work on targetry. But you dump your protons into this material, and then they scatter around and they produce mesons. So mesons are even simpler in some ways than protons. Protons are baryons because they have 3 quarks. Mesons have a quark and an antiquark. And they're lighter than baryons most of the time because of, they're made of less stuff. So these mesons can be produced, and because they're lighter than the proton, that's usually what they'll be producing in the scattering process, and you make a ton of mesons in this process. And then the mesons are also unstable, and then they want to decay. So a big way that mesons tend to decay is into muons. Almost primarily, they always decay into muons and a muon neutrino. And so from there, you have this big cloud of muons that are being produced by this target. But because your protons are slow, particles aren't boosted forward. And because your mesons are even slower than your protons, they're also not very forward. So you have this really huge cloud of muons that are not at all bunched together in the pin-tight way that we would need to collide them. So that's just the first step. And after this already extremely difficult to engineer and optimize step, you have something that couldn't even begin to be accelerated. But you have your muons at least.
And they're all negatively charged. So not only are they in a puffy cloud, but they're repelling each other.
Yeah. So this is something that we do need to worry about because of how tight we need that muon bunch to be.
Basically because you want to collide it into another bunch, and if they're all big and puffy, that's never going to happen.
Exactly, right. It's like colliding if you like BB pellets, right? Yeah. It's like the further away they get, the more diffuse they are, and the fact that you might collide one BB pellet with another after they travel some non-trivial distance is getting to be even smaller probability than what's reasonable to expect. So yeah, when you produce the muons like this, of course you get both mu plus and mu minus, and you scoop them off into their 2 different ways to process them. But yeah, once you try to crunch 10 to the 13 muons into a cubic millimeter of space, things start getting a bit tricky.
So is this something that we have the technology to do, or do we have ideas to do it? Is this an ongoing research program?
Yeah, so this is basically the biggest open question that we need to resolve as a muon collider collaboration. And so this is called 6D cooling, which sounds very cool. It sounds like, you're in higher dimensional space. And really what it means is the 6th dimension is 3 dimensions for momentum and 3 dimensions for physical space, because you need all these muons to be traveling not only at the same momentum, but also localized to a very small bunch. And so accelerator physicists have been working on this really for 30 years. And they've made a huge amount of progress, certainly in the last 10 years. But basically what they do is they design these different ways that you have to have this process of basically taking momentum from the muons, because you can't just squeeze them together. There's it's like squeezing one of those plastic dog toys, right? You squeeze it in one direction, it explodes in another direction. So you need to lose momentum from the system. And then you can use magnets to crunch it back together. So it's this constant process of take momentum, give momentum, take momentum, give momentum. And they need to do that basically 100 and some times before a muon even decays. And then you need to accelerate it. Right. So this is just the process of getting it ready to accelerate.
You have 1/millionth of a second.
And you have 1/millionth of a second.
And then, we're probably pretty good at the actual accelerating. I mean, that's something that we have been doing for a while.
You would think. But even that's hard. So accelerating particles that decay, again, are an entirely new challenge.
Okay.
Because one, everything in your detector is being constantly sprayed by the decay products. So there's all these other robust things that you need to account for when you're designing this. And the fact that we don't have the time effectively to do the same kind of acceleration that we do at the LHC. At the LHC, we just kind of ramp things up, and it takes 15 minutes to get those protons up to the speed. We don't have 15 minutes.
Don't have that time, no.
We have a microsecond. So the kind of magnetic field that you need to set up to make this feasible is also extremely different.
And I remember, this might literally have been before you were born, but I remember Chris Quigg talking about a muon collider many years ago. Chris Quigg, former Mindscape guest, and as well as a physicist. And there was something called the Ring of Death, because the muons, once they're in the circle, keep decaying and giving off neutrinos and other particles, which then go off and kill all the cows in the field.
Oh my God. I
around
love how dramatic we are
the
sometimes.
particle accelerator. Is this something that I should be worried about, or is that more or less something we have under control?
All right. Well, thanks, Chris, for saying that. Jeez. Yeah, I mean, it really cracks me up because neutrinos, when you talk about them in physics, most of the time it's just kind of like, who cares? Who cares? Neutrinos, like they're not going to get in your detector. Don't worry about them.
They go right through you.
But now that you can attach the word death ray or death circle to them, people are like, oh my God, neutrinos. So yeah, the physics behind it is that yes, neutrinos that are more energetic will want to interact more. And so we haven't had to worry about this in the past because we've never been producing TeV neutrinos in a large quantity. The worry that we would have is not that neutrino rays zap a cow and then suddenly it's raining steak. That's not quite the picture. But what can happen is that all of these neutrinos that are coming off from your muon being circulated is they'll just travel in a straight line, they'll escape the experiment, and they'll travel through dirt, right? Like they can just go through dirt. And if they're high enough energy, they might interact with some atom in the dirt, and they could excite the atom, and then that could decay. So it's the radioactivity of neutrinos activating atoms in the ground. So if this stuff is either sufficiently underground, or we have ways of absorbing the neutrinos before they, permeate too far, or something. Again, this is accelerator physicists are really, really great people that think of all kinds of wacky stuff that I would never have thought was reasonable. But you can, and this is the scientific term, you can wiggle the beam. And then when you do that, it's a diffuse enough beam that you're not activating any one patch of ground too much. And so the overall radiation dosage, I hate to be the person to tell you this if you don't know it, but you're always being irradiated. There are always things irradiating you. You just need a sufficiently small dose to not notice. So if you can do that, then it is in fact well below any sort of legal limit and dangerous limit that you might be approaching.
I mean, there might be a public relations problem here if you say, don't worry, we can wiggle the neutrinos so the deadly dose of radiation is spread out over a wider
just
area.
Wiggle it. Yeah.
Okay. I'm gonna
the wiggles.
I'm gonna trust that OSHA is on top of this.
I mean,
but all right, so I wanted to get the challenges on board, and I think we've done a good job with that. Unless there's any other secret challenges that we need to.
Yeah, I mean, there's failure is possible at every step. And I actually just got back from Fermilab yesterday to attend this really interesting workshop where people sort of get together and we're talking about what we need to make this happen. And someone showed this really beautiful table of basically all the ways in which we could fail and what impact that would have on the net collisions. And so, yeah, the steps of failure are first, we don't produce enough muons. So this targetry thing doesn't work. We melt the target by just dumping constant protons on it. That could fail. Cooling it could fail. We might not be able to, in fact, cool it quick enough to actually have a sufficiently high, a dense enough muon beam to get any sort of reasonable number of collisions out. So the cooling is by far the thing that could take us out the most. And that's the thing that we need to prove works before we actually make any sort of big steps to making the full-scale collider. So when people say muon collider R&D, basically we're talking about showing that this cooling and acceleration can happen. Right, the cooling or the acceleration around the actual ring is hard because, again, that requires an entirely new mechanism for accelerating things quickly. And then even just reconstructing the collisions is hard because, again, you have all these decay products shooting off of it. And how do you make sure that your detector isn't constantly overwhelmed by the electrons and neutrinos coming out of these decaying muons? How do you actually see the physics of the collisions and not just the physics of muons decaying? So that's also hard. And then, of course, neutrino death beam. Let's stay away from that phrasing. The neutrino radiation. can be mitigated with wiggles.
Well, and maybe again, just for cultural enrichment purposes for the audience, there's a kind of physicist whose job it will be to figure out, okay, how do we build a detector that can distinguish the actual muon collisions giving us new physics from sort of the background radiation and things like that. And then there's another kind of physicist who's in there with a soldering iron and building the machine. And there's another kind of physicist, I think like you, who is saying, okay, here's a model that makes a prediction that we could actually test in a machine like this.
Yeah, and there's also even a whole bunch of physicists that figure out how the magnets will bend the muons, right? So like really every sort of difficult problem we have, there's an entire specialty dedicated towards solving the problem. That being said, we definitely are a bit human power limited at this point. So if you're out there and you say, man, the thing I would love in life the most is to accelerate muons, oh my God, please call us.
Well,
Please.
it will take a while to do it, so we can get the youngsters excited about this, right?
Yeah, if you are 10 and you want to be a part of the most exciting human experiment ever made, please
There you go.
stay in school. We need you.
And okay, but let's switch to why this is worth all of the hassle. What's so great about a muon collider?
Yeah, so I mean, I think there's a lot of ways to answer this question, and I think all of them are kind of equally valid. So I think the most obvious answer that you can have is we are scientists and we want to know if you can do something, right? So this is a kind of collider that we have theorized, and there's no fundamental showstopper that would suggest that this is a deeply impossible task to do. So the fact that, this is just a scientific challenge to see if you can collide muons, and this could open up an entire new generation of colliders, which are really effectively microscopes, right, for the fundamental interactions. The fact that this is a possibility, to me, is worth doing, right? Like, if you can really open up an entirely new way to do a physics experiment, that's awesome. That in itself is very cool. In terms of understanding sort of the fundamental problems that we talked about in the beginning, again, what's exciting about muon colliders is this was kind of, if the technology can work, which I understand is a preposterously big asterisk to put on all of this, but if the technology can work, this is by far the fastest way to take us, the fastest and the most energy efficient and compact way to take us to that energy frontier. So given that we are kind of stumbling in the dark right now in terms of understanding where the Higgs comes from, what dark matter is, do neutrinos get mass from the same mechanism or a different one? Is there anything new about the Standard Model? Are there fourth generation particles? That one's a little bit wacky, but the fact that there are so many open questions and no one beautiful theory like we had for supersymmetry sort of explains them all, to me means that we should just be explorers. And we should be kind of agnostic and just do experiments in which we can sort of get the most return on our money in terms of just seeing new things. Mm-hmm. So going to that energy frontier, having a clean environment, getting high luminosity, that to me is how we're going to get unstuck in particle physics. So muon colliders being the fastest way, the cleanest way, and a really novel way to see things that we've never seen before makes it something that I feel like we have to invest.
And you use two words in there that sort of sound prosaic but are super important, which is compact and energy efficient. Maybe that's three words. But, compact, who cares how much space it takes? Don't you have space? And energy efficient, like, can you just plug it in? Why is that a big constraint?
I know. I think so much of physics, there's like the meme that they have, the midwit meme, right? Where it's like the bell curve, and then you have like someone saying something stupid on one side, and then someone saying something a little bit educated in the middle, and someone saying something, the same stupid thing, but with a lot of wisdom. And that to me is physics in a nutshell, right? It's like when you first start physics, you're like, oh my God, like the detector's underground. Like, what if the ground shakes? And then you're like, no, come on. People have gyroscopes and there's so much engineering and the machine is so heavy. And then you're like, oh no, but the ground shaking does in fact cause problems. And this to me is the same thing with like, space use and energy efficiency. At Fermilab, they're literally trying to plan what energy they can reach at a muon collider given the amount of space we have at Fermilab. Because if you don't own the space, you can't put a collider there, it turns out. If you are okay with us tunneling into your basement and you live in Batavia, again, please call. But yeah, like you just if you run into mountains, you run into underground rivers, you run into state borders. And so you just can't build an arbitrarily big machine and expect that, yeah, like you as a scientist are immune to property law. So that's something silly. And also just the cost of building a tunnel.
Hmm.
Tunnels are so expensive. Oh
Hmm.
my goodness. So the smaller you can get it, the cheaper it can be. And again, it's not, we don't live in a fantasy world where every scientific thing worth doing is funded. So if you could have something with a smaller tunnel that gives you a whole bunch of physics results, that's probably the way to go, you know? And with energy, I mean, I don't know how political we get on your podcast,
As political as we
but
want to get.
I mean, the whole Russia-Ukraine war, that is zapping Europe of all of its energy. And the LHC is even having reduced run capacity because there's just less energy to be had in Europe. And quite frankly, if you need to choose between warming people's houses and colliding protons, I understand I understand that tough sacrifice we have to make. So yeah, we live in a world where there's global warming and there's war and there's, you know, territorial issues, and the fact that we are scientists doesn't put us above any of these issues, and we still have to be responsible stewards of public money and space.
Yeah, that makes a perfectly good argument. I noticed you didn't say that you were actually in favor of shutting down or turning the LHC, giving it less power to help the Ukrainians, but you understood why people would be, which is, yeah, that's good. That's how physicists have to think, right? Because no one else is going to do it for us.
Look, Germans, use a blanket.
Yeah, exactly. So you mentioned Fermilab there. Does this mean that the U.S., like, I don't really honestly care in some sense where it's built? Australia, India, these are all fine places. But is the U.S. one of the places that is contemplating building a muon collider?
Yeah, so I think this is also something very exciting to me. On a personal note, again, since I grew up in Illinois, and definitely my parents were not physicists, but science supporters, generically, is having Fermilab close to your house. Just gives you an appreciation that things are dynamic, and it really, you know, it makes you feel much more energetic about the idea that, oh, I could do research, or that, you know, research is happening, and it definitely gives you a sense of, you know, excitement about it all. So, you know, I also have this kind of agnostic approach that, oh, I don't really care where it happens, I just want it to happen. But when you're close to it, it really, you feel it, you know, you really feel it, like, oh wow, like there's an energy in the air that's not neutrinos, and you get excited, and it's just, you know, cool to be a part of it. So this is something that's really exciting as someone who's currently doing science in the US, is the fact that the US might want to re-enter the world stage of particle colliders is amazing. And I think this is very indicative, and this might be the spiciest thing I say. So I think the styles of doing physics in the US and other places, Europe is kind of my biggest benchmark because of the people I interact with the most, but definitely the style of physics in Europe versus the US are very different. And I think in the US, for better or for worse, we tend to be sort of the people that always want to make sort of wacky theories, or just like make experiments measure things that they were not made to measure, and just kind of be, yeah, quite frankly, a bit of the dreamer. Is that, yeah, maybe we hand wave a bit and we don't worry so closely about the 15th loop correction, and, you know, we're a little bit sloppy. But the fact that, you know, then opens up the possibility of, like, oh, let's get weird with it in science, I think is something that I really like about the US atmosphere in physics. So if a place like China or CERN wants to go ahead and do a machine that's like the FCCEE, or the CEPC, then that's great. And the precision physics and really measuring the standard model, I think that that's very in touch with the science goals of those communities. But then doing the weird project that's like, well, can this even work? Do we know what we're doing? This is such a far off shot, and then maybe it'll happen, to me is very in line with sort of the American ideology towards doing physics, especially looking for new physics. So that to me is kind of the ideal outcome of everything is that countries that are much better about keeping track of factors of 2 and pi go for the precision machine, and then the Americans pool their resources to put a muon collider on their soil. But of course, all of these projects are international,
Sure.
and international collaboration is not only encouraged but required to pull any of this off. So where it ends up is not zeroth order, but it definitely it has an impact.
Yeah, I think it's a very good point. And it's not just that one style is better than the other, but a diversity of styles is very helpful. And especially when we're in a situation where we don't know exactly what we will see at this next generation.
Yeah, I think there's a lot of push and pull that needs to happen in the community right now, is that we need precision, but we also need discoveries. We need experimental evidence, but we also need motivating theories, and having sort of the most diverse pool of ways that we can sort of approach these problems that we don't really have a clear answer to or a clear way of proceeding on. I think that that's going to be the most robust way to find success.
And I remember seeing an interview with a scientist from CERN who, made the perfectly reasonable point that we're not building particle colliders that often. We built the
True.
LHC. It's going to take a long time to build the next one. And there's a very real danger that we forget how to do it, right? That, there's a lot of implicit knowledge that just sort of ages out if we don't do this regularly.
Oh, absolutely. There's no textbook that you can buy. There's no IKEA manual to how to build a particle collider. And so much of what's taught is just passed down between groups, and training individuals and things like that. So I think sometimes it's a little bit, I go back and forth about how seriously I should weight this, because part of it, if you just kind of sell it like that, then it feels like, okay, well, you just want to keep the field of particle physics alive so that you have a job. But it is much more profound, I think, is that if you want to keep particle physics alive so that there's the possibility to have a collider if we make a lot of progress in one area or another, then you need to preserve the knowledge.
And good. Let's wind up sort of by bringing it back to the physics goals here. Are there things that a muon collider would be specifically good at discovering if they happen to be out there?
Yeah. So I think again, this is something I've definitely become the person that I feel like wants to have a foot at least in both camps in terms of understanding sort of where these machines lie in terms of likelihood and progress and physics goals and things like that. So a muon collider versus an E plus E minus collider can have similar physics programs, but there's definitely strengths for one versus the other. So if you're just comparing E plus E minus and not like a future LHC at a much higher energy, the energy frontier is something completely new.
Yeah.
So if you just want to see new physics directly produced above, a couple hundred GeV, you need a muon collider for that. And if you want to see it produced with fundamental particles, you can't even compare it to a proton-proton machine. And just for comparison, right, if you were to build a 10 TeV muon collider, which sounds less than the LHC because that's 14, but because protons are composite, a 10 TeV muon collider would be comparable to the physics for the average collision that you can get out of something like a 70 or 80 TeV, if not more, proton-proton machine. So that 100 TeV number that you might hear thrown around by China and CERN would be comparable to a 14 TeV muon collider. So the fact that these are composite particles makes a big difference in terms of what energies are accessible. So the energy frontier, you just need it. And there's a million theories that you can test. You can do things that have to do with SUSY. You can do things that are just extensions of the electroweak sector. You can do things that are just completely new particles or dark matter related or things like that. And a lot of the times you just need higher energies to really see the effects of these particles show up. So the energy frontier, I think, is really the most compelling reason to say that a muon collider is something that we should invest in. In terms of other physics programs, as we said in the beginning, the Higgs boson is definitely the most mysterious particle. And depending on exactly your ideology, you may or may not say that a Higgs boson is new physics. But I'm not NEMA, so I'm not going to say that. But you can study a lot of Higgs bosons in a way that you can't do at the LHC, and you can do it in a much cleaner environment in some ways too. So, a 10 TeV muon collider, given the physics program that we hope to run, you can produce 10 million Higgs bosons. And with 10 million Higgs bosons, you can study a lot.
Yeah.
So, if you really want to flesh out the story about how the Higgs couples to itself, how it couples to other particles, how the symmetry is restored in the electroweak sector at higher energies, a muon collider is also a very good tool for that. So while the E plus E minus machine is usually what's billed as the Higgs factory, a muon collider could also have a lot of the complementary and overlapping physics program of that kind of machine too. So studying the Higgs and going to higher energies to give you the sound bite are really what we want to do with a muon collider. But those are basically the only two things that I even know what to suggest in terms of trying to resolve things like the hierarchy problem or dark matter or stuff like that.
Your day job is writing papers, thinking about models
That's
of
what they tell me.
physics beyond the standard model. We're recording this during the day, so I guess this is part of your job. But so, it's the end of the podcast. We can let our hair down. Do you have a specific favorite model that you have personally worked on or thought up that might be amenable to testing in some way? Just to give I want the audience to know what it's like to be a working theoretical particle physicist.
Okay, well, step one, have 3 cups of coffee and 2 existential crises a day. But okay, so my favorite model, I'll give you 2 answers to this. Sure. There's one model that I just hope is right, and I just hope is out there just because it'd be nice. So I really hope that there's a new Z prime or vector boson out there. So I want some new spin 1 particle that looks like a massive photon. We often will call that the dark photon or a Z prime. I just want that thing to be out there. I think having the existence of that particle would just open so many interesting questions, and it could be the portal to dark matter. It could be the portal to something else interesting. It could be something that mixes with the electroweak sector, and there's all sorts of new complicated stuff when we have to reinterpret everything. So I really hope it's out there.
So sorry, we know of the good old Z boson. There's only one of them. It's a neutral spin 1 particle, and you're saying a different neutral spin 1 particle with a different mass, but doing kind of similar things.
Yeah. Basically, a heavy photon is what we're looking for. And the reason that that's exciting is because whenever you have a spin 1 vector particle, it couples to something else. It's charged under something else. So it could be a portal into some whole new world of physics. And so this is the second answer that I hope that we find, is I hope that we find just an entire new sector of physics. It could be supersymmetry, it could be all the super partners, it could be that dark matter is an entire sector and not just a single particle that accounts for everything. I hope there's some new group of particles, and I hope they're strongly interacting, because I just think that would be super fun to work on for the next 50 years. So in terms of what I think is out there, well, I have no idea, truly. I think definitely things will have to show up between the energies that we can see and the Planck scale, which is that magic number that should set the Higgs mass. Something has to be out there. I just fundamentally can't reconcile a world where there's just 16 orders of magnitude that are empty, And I don't think that this is an accident. I don't think the universe is this way because, some supreme power fine-tuned some numbers and look where we are. I think there has to be some deeper explanation. So whether or not this stuff shows up at sort of the TeV to 10 TeV range, there are some predictions for that. Supersymmetry could be hiding in this range. There could be evidence that the Higgs boson is also a composite particle that could pop up at this energy. And really sort of the first real hint that we could see of new physics that would affect the electroweak sector is really 4 pi times the VEV. So that sits right around a couple TeV, around 3 TeV. Is that a guarantee? Absolutely not. But it's a way to start. So yeah, I don't know. I want to see something that messes with the Higgs. That's what I want to see. And whatever it is, who knows? But I think something's got to be out there.
So your calendar for the working particle physicist that includes 3 cups of coffee, 2 existential crises. It also
Yes.
has to include a sense of absolute grandiosity that we can figure all of this out. That it's something that is amenable to our understanding.
Yeah, I mean, I think I got into particle physics at a very weird time. So I am finishing my first postdoc, which means that I've been in the field for about 10 years. And in that time, I have seen the Higgs boson discovered and supersymmetry not discovered. I have seen the Tevatron shut off and the LHC turn on, and the plans for the High Lumi LHC to go on. And now, I think people have tried to convince me throughout this entire career that I've had that particle physics is dead. We don't know what we're doing. Give up and do cosmology or biology, as you suggested earlier. And I just think that can't be further from the truth, because what amazing privilege I have as a young person in this field is that I get to be part of the conversation of how we unstick ourselves, right? Is how we decide what the next generation of experiments gets to be. And we get to shape this idea of, well, how do we look for new physics? And, to have my whole career, well, most of my career in front of me as we go through this era of absolute, change and really first order changes in how we're going to approach particle physics. I think it's an exciting time to be a particle physicist. I don't think that's a very popular opinion, but it is what I have to tell myself every day to get out of bed and start my existential crises and brew that first cup of coffee.
With very good reasons, it sounds like. Cari Cesarotti, thanks so much for being on the Mindscape podcast.
Thanks, Sean.